All right, now we're going to move on to modeling motion using equations. And more specifically, we're going to narrow our focus on the case where acceleration is constant. We'll find out that this is a pretty reasonable assumption to make in most cases, assuming constant acceleration, that is. It has to do with the idea of a force, but we will see that in many cases, objects will accelerate at a constant rate. So this is a pretty important special case to know. So we will call these the big four equations of kinematics. And these apply anytime the acceleration of an object is just a constant. So as long as the acceleration is just the same all the time, we can apply any of these four. So you'll notice there's lots of different variables we have. We have displacement, we have initial and final velocity, we have time, and we have acceleration. So why there's four of these is each of these equations are missing one of the variables. And as a result, the variable that you don't need and don't have tells you which one of these four to use. So, for example, if you have a scenario and you don't care about how far the object went, you're probably going to use the first one. But if you know nothing about the time interval, you're probably using the fourth one. But all of these are true in all of the uniformly accelerated cases. It's just there's one that's going to do things more efficiently. So, the key here is that all of them have exactly four kinematics variables, meaning three kinematics variables unlocks your equation. And then you can get the other two using any of the big four. So three variables is what we need. And the one that's missing tells you which one is most efficient for solving your scenario. And the missing one isn't the one you want to find, obviously, that doesn't help. So you might have to do some algebra and rearrange each of these to get what you want, but this at least tells you which equation to start with. So we're going to start by deriving these. So we actually need very little to prove these. So the first one, this is the only hand waving we're going to be doing, is the only assumption to derive these equations is that the acceleration is constant. So this is the only thing we need to assume, and all the kinematics equations can come from that. So we're going to use a graphing argument to just justify that the velocity should follow this form, where the velocity at a given time is just its initial value plus acceleration times time. So there's a reason we did this after the motion graph segment, because we learned from motion graphs that acceleration is the slope of velocity. So if acceleration is constant, this means the slope of v is a constant. And more specifically, the slope is a. So if we look at a graph of velocity as a function of time, all we know is that the slope is constant. We know nothing about where the velocity starts, so we can just give it some arbitrary starting value, but we do know that it has constant slope, which is equal to acceleration. So as a result, it's a straight line, so we can model the velocity function as y equals mx plus b. What are we modeling? We're modeling the velocity. What is the slope? The slope is the rate of change, which is a in this case. Our independent variable is time. And then what's our y-intercept? Well, it's just our starting value, which would be our initial velocity. So that's how we can justify our first kinematics equation. And now from that, everything else can be derived. So now let's use that graph that we came up with. And using the fact that displacement is the area under this graph, let's get a displacement equation. So we're saying that our velocity function looks like this. So this is v, this is t. And we're looking more specifically how far you've gone just after a time of interest, t. And we know that the displacement is the area under this curve. So we do know that delta x is going to be the area. And if you know that this is a trapezoid, you can get the formula really quick, but I think I'll show it by breaking it down, because we can break up this trapezoid into two shapes. So first, there's this rectangle, and then there is this triangle stacked on top of it. So we know that this is going to be the area of the rectangle plus the area of the triangle. So we need to start filling out some dimensions here. So the height of the rectangle is just going to be whatever this point is right here. Well, it's the y-intercept of our graph. So we know that this height is going to be the initial velocity, v0. I can do better than that. Let's just do this. And then we also know that this height is the velocity at the final time. So this height of the triangle would therefore be the difference in those two. Because if I know that v0 plus this purple segment, if the green plus the purple segment must equal v, then this is just v minus v0. Let's start filling in. So the rectangle area is going to be just base times height. And the triangle area is 1/2 base times height. And those could be different. So for the rectangle, the base of the rectangle is t, and the height of the rectangle is v0. And for the triangle, the base of the triangle is also t, and then the height is just the difference between v and v0. We're just doing segment addition here, right? Because if this is v0 and the whole thing is v, the difference must be that remaining segment. And now we're just going to do some algebra. So we get v0t plus 1/2 vt minus 1/2 v0t. And that will give us the result we're after once we simplify and do a bit of factoring, because we end up with 1/2 vt. v0t is 2/2 v0t, so 2/2 minus 1/2 is plus 1/2. And everybody brought a 1/2 and a t, so I get 1/2 t, or t over 2, times v0 plus vf. And that is the second kinematics. There isn't like a well-defined order. Like this isn't officially called kinematics number 2, but I like to just refer to them that because we don't really have specific names. Also, notice that this can also be written as v average times t, because I could write this as v0 plus vf divided by 2 times t. So this is actually v average times t, because I have v0 and vf. I'm adding two velocities, and then I divide by 2, so that is an average. And I forgot, we don't use the subscript f. So, okay. All right, now we just got some algebra, so we're just going to be plugging stuff in. So we had delta x is equal to t over 2 times v0 plus v. But earlier, we derived our first kinematics for v. We said that v was equal to at plus v0. So we can just plug that in for v. We can combine like terms inside and get 2v0 plus at. And then we can do some distributing. And we get the 2 and the 1/2 cancel there. So this would be v0t. And then I would get AT squared over 2. So then just writing this in our standard form, we'd get delta x is 1/2 AT squared plus V0t, which is a kinematics equation. This one's useful for modeling position as a function of time. And also notice this one, if acceleration is 0, we get distance equals speed times time. So it's consistent. And then we just got some substituting to do. So I want to continue the chain here. That might actually be easier just to substitute in. So we know the last equation doesn't have time in it. So if I start with delta x equals t over 2 times v0 plus v, if we can substitute away for t, we should be able to get our last equation. So we do know that v equals at plus v0. So v minus v0 equals at. So t equals v minus v0 divided by a. So we will plug that in. E. So v minus v0 over a divided by 2 times v0 plus v is equal to delta x. We can do some simplifying. So the cleaning up this right side, we get v minus v0 over 2a times v0 plus v is equal to delta x, or 2a delta x equals v minus v0 times v plus v0. So this is a difference of squares. So we could write this as v squared minus v0 squared equals 2a delta x. And then we get our intended results. V squared equals v0 squared plus 2a delta x. So a lot of algebra and symbol crunching there, but we have proven all 4. So notice we got exactly the 4 kinematics that we expected to get. So now we'll show kind of the method for solving the kinematics. So you'll get better at this as time goes on, but I just call it the laundry list method. I know in other countries, they refer to this as like the Suvat equations because they use U for V0. But this is sort of our laundry list setup, and I should probably copy this to save time later. So we want to list things. If you have 3 variables known, then you're good. All right, a box has initial velocity 1 meter per second. Okay, that's pretty clear. Very clearly VO. And slides down a ramp with a uniform acceleration of 0.5 meters per second squared for 8 seconds. Calculate the final velocity of the box. So what I want is V, which means I don't want delta x. So I can check my big 4 and see which one does not have delta x in it. And it is the velocity time function. So I know that I want V equals V0 plus AT. And then it's just plug and chug. So this is why people pretty much like kinematics, because it's usually straightforward. There's a nice little formula that gets everything done. Just like that. Now, you could have to do some algebra. It's not automatic that you're just going to plug and chug. You might have to rearrange, as we'll see later. But this is generally the method. So laundry list out. Do that just for each of these. Rid of my extra dots here. All right. Runner speeds up uniformly from 3 meters per second to 6 meters per second over 10 seconds. Should be using blue. Calculate the distance traveled by the runner. So that means that we have no acceleration. Now the accelerationless equation is this one. And we can actually just plug and chug again. I've been nice not making you rearrange these so far. Just a nice 45 meters. All right, car accelerates from rest. So be careful when you're seeing start and stop. Like that actually does give you a piece of info. It gives you one of the velocities is 0. It accelerates from rest at a constant rate of 4 meters per second squared. And travels a distance of 18 meters. Calculate the time required to travel this distance. So I do not care about the velocity it ends with. So I need the VF-less equation, and that turns out to be the displacement time function. So here we can just plug in and we'll see that it's not instant. We have to do some algebra. It's okay to not do these symbolically. I'd probably say just plug in if you have all the numbers for these kinematics ones. Usually I'm symbols first, but if it's a numeric kinematics, just do this. 18 equals 1/2 times 4 times t squared plus, oh yes, that is why we're not doing this symbolically, plus, oh, it's 0. It's always nice when the 0 wipes out the linear term in this. It makes your life so much easier. So we get 18 equals 2t squared. Half of 4 is 2. Divide both sides by 2. We get 9 equals t squared. So t equals square root of 9, which is 3 seconds. No plus or minus usually in physics. Is usually the times we're dealing with, or times are always positive, but usually the negative root doesn't make sense. What we want. All right, truck is traveling 20 meters per second when the driver applies the brakes. The truck comes to rest after skidding 50 meters. Calculate the acceleration of the truck. We do not have time. Well, the timeless kinematics, the time-independent kinematics, as we often call it, is this one. Final velocity is 0. Initial velocity is 20. I don't know A. And delta x is 50. I get 0 equals 400 plus 100A. So I'd get 100A equals negative 400, and it does make sense that we get a negative acceleration, because in these 1D problems, they're moving to the right but slowing down, so acceleration should be to the left. So that's how you handle just these kinematics questions with numbers. Find the missing variable, and whichever one is not relevant to your problem tells you which of the big 4 is most helpful. Although they are all true at all times, they're just not always useful, as long as acceleration is constant. And our first caveat to that would be multi-segment motion, where there's just multiple different things happening in a sequence. So how this works is that you can't do kinematics overall because there will be different acceleration segments. But what you can do is a chain of kinematics, where the final velocity of one segment will be the starting velocity of the next. So that's the link, because you'll see that you won't have enough info unless if you figure out the linking velocities. So first, we got a cyclist. They accelerate from rest at a given rate for 20 seconds. They maintain this constant speed for 70 seconds after that, and then they slow down at a uniform rate, causing them to stop after another 10 seconds. So it says that we actually can't find the total displacement using kinematics once, but I see constant accelerations. So why is that true? Well, yes, it's true that this is a constant acceleration. This is a constant acceleration of 0, and this is a constant acceleration. They're not the same constant acceleration. So we have to do 3 separate kinematics applications. Bad me with the grammar. Apostrophe should be elsewhere. Whatever. So anytime you have a segment, we're trying just to link the segments. So we want to calculate the speed of the cyclist at the beginning of segment 2. I might call this delta x1, and I'll call this v1 and 2, just to show that it's like the linking velocity. And acceleration t. Okay. Accelerates from rest, so 0 meters per second. 0.25 meters per second per second. 20 seconds. Even though it might not be told, we're always interested in the linking velocity between segments. So we don't care about the displacement right now. Now, I'm sure a lot of you could actually determine this without kinematics. I mean, you are doing kinematics in your head, but you just don't realize it. But we'll do it and then show why the answer was probably obvious. We're going to use this one because we have no delta x. They start from rest and they accelerate 0.25 meters per second for 20 seconds. Multiply that out, we get, man, 5 meters per second. That was rough. That was a rough one for me. So you could have figured this out without kinematics, right? Because they start at rest and then they gain 1/4 of a meter per second every second, and they do that 20 times. So it's just going to be 20 times 1/4, or 20 divided by 4, which is 5. So now let's calculate the displacement of the cyclist on each of the intervals. Segment 1. Well, we just figured out everything about segment 1, so we can pick any kinematics we'd like with a delta x in it. You could show that any of these work. I'll use this one. So they accelerate for 20 seconds. They started from rest, and they ended at 5 meters per second. So that is going to be 50 meters. I actually definitely know that's right, because if they went 5 meters per second, which is their final speed for 20 seconds, they would have gone 100 meters. And it's actually a nice property that if you accelerate from rest, your average speed is exactly like the midpoint, your initial and final speed. That would be equivalent to going 2.5 meters per second for 20 seconds. All right, segment 2. What do we know about segment 2? Maintains this speed for an additional 70 seconds. So what we actually know is that the speed is constant. So acceleration is 0. So we could just do kinematics with a equals 0. But if you know the velocity is constant, there's only one equation it could be. It's delta x equals vt. So they're maintaining their final speed of 5 meters per second, and they're doing that for an additional 70 seconds, which gives us 350 meters. Right? Because their velocity is now constant. So we just go 5 meters every second, 70 times. And then segment 3. What do we know about segment 3? They slow down at a uniform rate, stopping after 10 seconds. So we do it again. Messing that up. Segment 3, we're interested in this. This delta x3, we do want that. Their initial velocity is 5 meters per second because at the start of segment 3, that is the end of segment 2, so the linking velocity is 5. We end at rest. We don't know the acceleration, and we don't care about it. And we do know that it takes, what did it say, 10 seconds? 10 seconds. So we're going to use the kinematics we used last time, the accelerationless one. Need to get my notation straight. I've been used to just doing VF. I've recently switched. Uh, 25. Which is exactly half of the original segment, which makes sense. Because you slow down twice as fast as you sped up. All right, higher 100-second interval. This is just the sum. So I went 50 meters, then I went 350 meters, then I went 25 meters. So I get 425 meters total. All right, let's sketch their velocity as a function of time with each segment being labeled. So we had the acceleration for 20, then we had constant speed for 70, then we had slowing down for 10. So our max speed was 5 meters per second, and that was achieved after I do have a red one actually. Red one. Can I make this just solid, please? No. I need to a little better. Then we maintain it for 70 additional seconds. So that goes to 90. And then we stop after 10. So here's the segments of our motion. So we see that it's definitely steeper on the way back. All right, verify that the total displacement of the cyclist can also be found using the velocity graph. Well, delta x would just be the area of the velocity graph. So we can break this into 3 segments if we would like. It does want this. This is segment 1, this is segment 2, this is segment 3. It's a very skinny triangle. Segment 3. All right, segment 1. This is 1/2 times 20 times 5. Segment 2 is just difference between 20 and 90 is 70, so 70 times 5. And then this one down here is going to be 1/2 times 10 times 5. And notice we do get the segments we expect because each of these areas is going to be the displacement on the segments we calculated earlier. So half of 20 is 10, times 5 is 50, 70 times 5 is 350, and 5 times 5 is 25. So notice we do absolutely get 425 meters as we expected to get. Now, this is also a trapezoid. Is this a trapezoid? Yeah. You could have found this with the area of a trapezoid, and that also would work. So again, I've been kind of not acknowledging trapezoids exist, but the area formula of a trapezoid is h/2 times b1 plus b2. So for this trapezoid, the height is the 5 meters per second. and base 1, the long base, is 100. And then the skinnier base would just be the flat top segment, which would be 70. And I actually have to check this. So that'd be 2.5 times 170, which is definitely 425. So if you do know the trapezoid formula, you can save yourself from breaking these up, but I actually like that it makes you visualize each segment. All right, now we got some symbol math to do. So you might not be giving numbers, but instead you have to do some symbol manipulation. So consider a 3-segment motion like before. We accelerate A for a distance d, then we accelerate 2a for a distance 2d, then we stop over a distance d. We want the time required to stop during segment 3. Okay, so what we want T3. So if we look at our list, we'd get something like this. And we know that the thing we want is T. And we also know that it travels a distance D. And it stops at the end. Notice this is not enough info to solve, because we don't have 3 variables, we only have 2. And as we said before, the key is to do enough linking where we get that intermediate velocity. Our key here is that we know we're not going to be able to get the acceleration yet, because we're not going to know the speeds, so we need to get the speeds. So we'll just sort of do a chain here. I'm going to start skipping the laundry list, just because I think that's something we're going to figure out here. So notice that here we have no t, and here we also have no t. So that means we're going to use the time-independent kinematics for each of those. So here we're going to look at segment 1 to segment 2. We started from rest. Our acceleration was a over a distance d. So this means the velocity at the 1-2 transition would be square root 2ad. Now we can link it up again, where we do the same idea. Look at our velocity from 2 to 3. Because now we figured out the initial velocity in segment 2. It's just going to be the starting velocity, or ending velocity of segment 1 is the starting velocity of segment 2. So we can just do it again. Where v squared equals v0 squared plus 2a delta x. And our initial velocity is square root 2ad, so square the square root gets you 2ad. The new acceleration is 2a, and the new distance is 2d. So we get 2ad plus 8ad, which makes 10ad. So the velocity connecting segments 2 and 3 would be square root 10ad. So notice this is just sort of a chain here. So now we go all the way here, just to say that VO is square root of 10 AD. And now we just pick a kinematics to use. Well, acceleration is missing. So we want to find time. So missing acceleration means we're looking at this one. Delta x equals t over 2 v0 plus v. So d equals t over 2 times square root 10 ad plus 0. So 2d would be equal to square root 10ad times t. So t would be equal to 2d over square root of 10ad. Oh, do we simplify this? You don't have to, by the way. I think we will. I think we will, because some people would like to. No, I'm not going. Yeah, I'm not doing that. That's an exercise for the reader. Notice the only symbols I was given are A and D, so those are the only symbols that appear in my answer. I think you get some sort of, probably like a 5 something in here. And you'd end up with a D in the numerator, the square root. Let's try it. You get 2 divided by square root 10 times square root of D over A. Don't rationalize the denominator. Only fools rationalize the denominator. There is no reason to be doing that. Well, that's kind of a tricky one. Lots of plugging in going on here. But it's good symbolic derivation practice. All right, so now we have position time functions, where remember when we modeled motion, where velocity was constant, we said it's straight lines. Well, when acceleration is constant, we modeled using parabolas or quadratics. Notice that in the special case of no acceleration, it's just y equals mx plus. So now we're going to revisit one of my favorite little QQT problems, where we had the two runners passing each other. Now we have two cars that are going to collide. So car A starts at x equals 0, 20 centimeters per second initial velocity, and accelerates at 40 meters per second per second. Car A will be accelerating at 40 centimeters per second squared to the right. Car B, same idea, except it does not accelerate. So it has the same initial speed, just the other way. So it's a head-on collision, except car A is also accelerating. So they're going at each other at the same speed initially. Car A accelerates. Our first question, where do they crash? Do they crash on car A's side, car B's side, or right in the middle? I guess that's not an option. So where do they collide? Well, we know if everything was symmetric, they would meet right up in the middle. But it's not. Car A is accelerating. Car A is getting faster and faster and faster and faster, but car B is stuck at its initial speed. So we can use the same argument we made with the runners. So the faster runner reaches the midpoint first, so the collision happens on the slow person's side. So similarly, we can say that since car A is speeding up, car B is not, and they start at the same speed, car A will always be faster than car B, so car A will reach the midpoint first. So the collision is going to be somewhere on car B's side. That puts us in the right range. So let's sketch a graph of the position of each car as a function of time, labeling each curve. So for car A, we know it starts at 0 and accelerates. It's going to be something like that. And then car B, because car A goes in the positive direction, so it would be a line with increasing slope, and then or a curve with increasing slope in the positive direction. And car B does not start at 0, it starts with an intercept, but it moves at constant speed. So car B doing this, they're going to crash somewhere closer to car B's spot. So now we're going to just make a function that models each of these. So notice we're expecting A to be quadratic and B to be linear with negative slope. So our general form, we said, looks like x equals 1/2 at squared plus v0t plus x0. That's just our first kinematics. So xa is going to be 1/2. Its acceleration is positive 40 centimeters per second, t squared, plus its initial velocity is positive 20 t, and it starts at 0. xb, 1/2. Its acceleration is 0, t squared, plus its velocity is 20 centimeters per second in the negative direction, and it starts at 300. So we can simplify these to get xa equals 20t squared plus 20t, and xb equals 0t squared, so we're not even going to include that, negative 20t plus 300. So we do get what we expect, right? We have a quadratic that's concave up, and we have a line with negative slope with a y-intercept. All right, when do the cars collide? Well, we're going to do what we did last time, where we just set their positions equal. So we get 20t squared plus 20t equals negative 20t plus 300. Add 20 to both sides, and we get 20t squared plus 40t minus 300 equals 0 when we put everybody on the same side. And you could Desmos this, of course, but I design everything to work out nice. So we're going to take out a 20 from everyone. We get t squared plus 2t minus 15 equals 0. Yeah, that definitely works, because now it's just a factoring question. Can I think of two numbers that multiply to negative 15 and add to 2? Yeah, because it's 5 and 3. So I can do plus 5 and minus 3 equals 0. So I get two solutions. The cars collide at negative 5 seconds. Okay, it's definitely not that. Or the cars collide after 3 seconds. So the negative time root is rarely meaningful. All right, calculate where they collide. Well, I can just take the position of either car at 3 seconds. I'm going to do the linear one so I don't have to square anything. So xb was just negative 20t plus 300. So I get negative 60 plus 300, which is 240 meters. And notice that is definitely to the right of the midpoint. So our selection was definitely correct. Now we'll look at a couple special cases. Justify using a graph. Car A and car B are both launched with the same initial speed towards each other, but neither car accelerates. Well, that's going to be pretty straightforward. So that would just mean car A moves at constant speed, car B moves at the same constant speed. Where do they collide? Right in the middle. Same idea, they're both launched at 20 centimeters per second towards each other, except now they both speed up with the same acceleration. You can probably guess where this is going. So car A is going to look like that. And then car B is also going to look like that, except reflected. No, not like that. I'm not good at drawing this symmetrically. Something like that. Once again, they're going to collide right in the middle by symmetry. I will try to fix this. Good enough. Good enough. It's supposed to be symmetric, whatever. All right, a special case of kinematics is free fall, because what's the first thing we learn about free fall? It is a constant downward acceleration. So, kinematics applies. And there's not a lot of shortcut formulas that I suggest you know, but this is definitely one of them. So, if you drop an object, again, drop, an object begins from rest and falls. Only then can you use what I call the free fall equation. So the height that you have fallen is equal to 1/2 times g, which is always 10 meters per second, times t squared. We will make g positive. So you can apply negative signs if you, depending on your coordinate system, but the number g itself is positive. So it only works if you are dropping an object. And this is really nice because if you know the time you spend falling, you know how far you fell from. If you know the height, you can calculate the time it takes to hit the ground. So let's prove this. We are claiming that this is a special case of one of the big four. It is pretty easy to guess which one it's going to be, right? Because it has a 1/2 and a square in it. So we'll use, in the y direction, we'll use the 1/2 at squared equation. So we get this. And what we said is that there is no initial velocity. And usually for these, unless if you're tossing an object upwards and it returns to the ground, it's usually okay just to say that down is positive. Doesn't matter. So the distance you've traveled in the y direction is 1/2 times our acceleration, which is g because we're in free fall, plus 0. So delta y is just 1/2 gt squared. And what is delta y if not the distance h that you have traveled? So this is a very good equation to know. If you are dropping an object, this always applies. So if an object starts falling, as soon as you start the timer, this equation applies. It does not if you're tossing an object up or throwing an object down. So now we're just going to play around with some free fall kinematics. So this is actually easier than the ones we've done before, because when you're in free fall, you know that acceleration is absolutely going to be 10 meters per second squared. All right, a rock is dropped from rest from an initial height of 45 meters. Calculate the time required to hit the ground. Well, we have height, we want time, it's free fall. You can't actually just skip right ahead to h equals 1/2 gt squared for this one. So 45 equals 1/2 times 10 times t squared. So half of 10 is 5, so 9 equals t squared. So t equals square root of 9, which is 3 seconds. A rock is launched upwards from the ground at 40 meters per second. Calculate the time required for the rocket to hit the ground. Okay, so here's a case where we actually have to take the sign into account. So we'll laundry list this one because this is not h equals 1/2 gt squared because there's initial velocity. So we'll laundry list it. So first, we know we're launched upwards at 40 meters per second. We want to calculate the time required to hit the ground. So we know we need time. We do know that the acceleration is 10 meters per second. But if we're tossing the object up, we know that that acceleration must be opposed to that. So that acceleration is down. So if you have an object moving up and down, you probably want to make g negative. The acceleration negative, rather. So we need a third variable. So an object is launched upwards from the ground, but then it returns to the ground. So actually, we can figure out from symmetry here that there's actually no displacement, right? If it goes up and goes down, it's right where it started. So that's why this can be tricky, getting that one. You could have also done symmetry and figured out that its velocity would also be negative 40 meters per second. That's another trick. So we could just go ahead and do that. So delta y equals 1/2 at squared plus vy0t. 0 equals 1/2 times -10 times t squared plus 40t, which is -5t squared plus 40t, which is equal to, so 0 is equal to -5t times, oh, we'll keep the, yeah, we'll factor out the negative. -5t times t minus 8. That means the rocket hits the ground at t equals 0. Well, of course, it started there. Or t equals 8. There's also some clever things you could do with the velocity where you understand that the velocity actually is 0 at the top. So you could have used a different equation to figure out the stopping time, which is half, double it. This is another way of doing it. Also, you probably just could have seen this. There's just like a think about it way. Launched up at 40 meters per second. Every second, you lose 10 meters per second as you go up. After 4 seconds, I would stop, and then I double it by symmetry to get the total time. Then we'll do some symbol math. Ball is dropped from a ledge of height h. Find the impact speed of the ball. Okay. Well, it's dropped, so some things we know is that v0 is equal to 0. We know that the acceleration is given by g because it's free fall. And we know that delta y is just going to be h. I'm not tossing it up, so I can make everything positive. Notice that there's no t. There's no t in this equation. So I can use v squared equals v0 squared plus 2a delta y. So v squared would be equal to 0 squared plus 2 times g times h. So v squared would be 2gh, or v is square root 2gh. This result shows up a lot, and we will understand kind of a fundamental reason why this pops up a lot. All right, tennis ball thrown vertically upwards at a speed v0. Determine the maximum height reached by the ball. Well, no time again, so it must be this. So now we have some thinking to do. Well, we know we're throwing it upwards at speed v0. And if we're traveling upwards, we're slowing down. So that acceleration should be -g. And we know we're interested in this distance, h. So we must be able to figure out what the speed is in the y direction at the top. What would that be? Well, if we think about our picture, we would always get something like this. For the middle, this is your turning point, so Vy is 0 at the top. This is a really important fact for anything free fall. When you're throwing something, the top of the trajectory, the y velocity, and only y velocity, is 0. So 0 equals V0 squared minus 2gh. So V0 squared equals 2gh. Oh, that's interesting. That's the same thing we got last time, rearranged. And then h would therefore just be equal to V0 squared over 2g. Not a coincidence that those are reverses of each other. All right, last thing we'll do. This is strange. This is a physics-specific thing we do. We'll do it many, many times. This is the first time we'll do it. This is known as linearization, where we want to calculate something using a best fit line, but the data is not linear, so we can't draw a line. So instead, what we do is we figure out a way to force the data to be linear. So if you're just given like a y equals mx plus b, if I graphed x versus t, I can see, oh, v is in front of the independent variable, so that's the slope. X0 lives by itself, so that's the y-intercept. So what we're going to do is we sort of trick the formula into becoming linear by shoving all of the variables into these y and x boxes. It's just most clear from context what we'll do. So for example, x equals 1/2 at squared. That is definitely not a linear model for x and t, right? We know that curves up. But what we could do is we could be clever and say, okay, well, the non-linearness is coming from the t squared. So there's nothing wrong with x. So we could put x in its own box as one of the variables. But the issue is the t squared. And it's not the t, it's the t squared. So we shove the t squared also in a box. And now we have essentially forced our equation to be linear because it looks like we have something equals constant times something else, which is linear. So that is generally our technique, is you figure out how to shove all your nonlinearity into a box, and that's how you make y equals mx plus b come out of it. You often have like a lot of choices. Usually you can just graph sort of the function with like the exponents applied where you need. I don't like to deal with square roots, so I will always square by myself just to get rid of a square root. So I think we'll just show from context what I mean, because this is a bit theoretical. All right, so we're going to linearize this two different ways. We want the blank versus blank and what the slope and y-intercept of our model should be. So the slope will be the number in front of the x, and the y-intercept will be any pluses or minuses. So notice we cannot graph h versus t because of the square. So notice my variable is going to be h and t, because g is always just a known constant. I guess you had to infer that. I should say. I think it's clear from context, but I think I should say that we're given h and t. So h is fine. I can put h in a box by itself. And also, 1/2 g, that's a constant. So that is also not a problem. You can also live by yourself. But the issue is the t squared. So if the t squared wasn't a problem, we'd have a straight line. So I can just actually force the t squared to be its own little box. And this is linear, because I can call this my y, h is my y, I can call t squared my x, and then the number in front of the x would be my slope. So you are literally just putting all the nonlinearity in a box. So this is one possible approach. I'll show you some other ones. So I could graph h versus not t, but t squared. The whole object t is squared, meaning the slope would be 1/2 g, and there is no predicted y-intercept. Now that's not the only thing you could do. So what we could do instead is we could have once again had h equals 1/2 g times t squared. Something I like to do is usually you're solving for some constant in the slope. So I actually like to move some of the constants around so the slope is just my answer. So since multiplication, order doesn't matter, I can just rearrange some things here. I can instead write this as h equals g times 1/2 t squared. And notice now I can box that up, and it just gave me a different choice. So this is my y, this is my x, and this is my slope. So notice I picked a different choice, so I get different slopes out of it. So h versus 1/2 t squared gives me a slope of just 1g versus a slope of g over 2. I call this the slope purist method, where you just want like the constant. You want your slope to be as simple as possible, so you graph nasty things. There's always a trade-off. If you graph the simplest relationship possible, your slope will have a million symbols in it. If you graph the most complicated relationship possible, you can get a slope with just a single symbol in it. Now, this isn't the only thing you could do. You could have graphed square root of, you could have graphed like t versus square root h. You could do this. So order doesn't matter either. If you graph these on the opposite axes, you would just get an upside down slope. So there's a million ways to do this. Then we have v equals square root 2gh. So I'll show you why I hate doing square roots. So this is definitely not linear because the h is stuck under the square root. So we can use square root properties here, because square roots can be broken by multiplication, like this. That's just a algebra property. So now that gave me my first set of boxes. nothing was wrong with v, so I can just keep that in its box. And h is under the square root, but now I've banished it to its box, so I can graph square root h, and then my slope is square root 2g. So this is why I don't like dealing with square roots, because you'll get like some nasty slope expression with square roots in them. So I can graph v versus square root h. That would make my slope square root of 2g, and there is no predicted y-intercept. All right, now I'll show you my preferred approach for this. So what I like to do if there's square roots is I like to just square both sides. Right? You can do anything you'd like to both sides of an equation, and I hate square roots, so let's square both sides. So I get v squared equals 2g times h. So I can box this up. The square makes that nonlinear, and the h is now linear. So I get slope. Again, it's a personal preference thing. Now, if you're a slope purist using this method, you could also associate the twos like that. This is a valid linearization. That is your style. You could do that, where the slope would just be g. But that's kind of just our approach here. So this is a free response type, where you're given a data set, and you need to come up with an equation, come up with the linearization, graph the linearized model, and solve for the quantity of interest. And this is the poster child of things we want to solve for in physics. There's a million ways to calculate g. It shows up in like every formula. So you'll calculate g a lot. Students drop a ball from various heights h. So they are picking different heights h to drop the ball from, and then they record the time required. So we can guess what formula will apply here. But it says the big four can be applied to this scenario. So why is this a kinematics problem? The big four works? Well, this is free fall. So since it's in free fall, acceleration equals g, which is a constant. So kinematics apply. All right, sometimes it's derived, sometimes it's determined. Like if you just know the formula, I can just say like do the formula. So what is a quantity that relates fall height and fall time to g? So usually this means these two variables are going to exist on opposite sides, and then the constant you want will also be in there. Do not solve this for the constant. You want these two things on opposite sides. So h equals 1/2 gt squared. I'm done. That's my formula. This just says get me a formula that has the two table variables in it and the thing we want to calculate. Right? We have lots of data for h, we have lots of data for t, and using that we can somehow get g. So what can we graph to determine g? It's your choice. There's not a wrong choice as long as it's linear. The one that I think is most natural, since our equation is h equals 1/2 gt squared, would be what I say is like the simplest thing you can do. Or nothing nonlinear about h, so h can live in its own box. 1/2 g, those are constants. And the thing that's nonlinear about t is the square, so we got to keep the t squared in the box. So this means that we're graphing h on the y-axis. We're graphing x, or t squared, on the x-axis, so our slope is 1/2 g. You can actually just stop there. This is actually how I prefer you write your free response when we ask you. This is completely valid. You don't need to say, on the y-axis, put h. On the x-axis, put t squared. This is very clear what you're doing. So now we have our favorite running joke. And this is where I say I do the mining off camera, because you do not want to watch me plot points and draw a best fit line. We want to actually analyze the scenario. So this is how you get your 4 points, the easiest 4 points on the free response of this exam. You label the axes with your linearization. So we want h and t squared. We have to put numerical scales. A scale requires multiple ticks. You can't just put one number in each spot. Plot the data points, draw a best fit line. So what's new is that you're not graphing h and t. You're graphing h versus t squared. So you'll have to create a new data table and do it that way. So here's the mining off camera. So notice that I switched my data table around because I wanted t squared on the x and h on the y. So I literally just squared all the t's by hand. I didn't do it by hand, I actually Desmosed it, which I will show you as our last thing that we do here. And I plotted it. So I got my first point by putting the quantity with units. So height is in meters. T was in seconds, so t squared is in seconds squared. You'll get some weird units, that's okay. I don't care that I don't know what a squared second is, it's fine. And then I plotted with numerical scales. Now, I write these to be pretty easy to graph. And how I rounded it, it was just straight up linear. And then I draw a best fit line. Best fit line should like overestimate half the data and underestimate half the data. It should not be forced through 0, 0 or anything. It should just go half above, half below. This is like extremely linear. And then after doing that, Desmos spit out my best fit equation. So these were my x and y. And Desmos spit out this as my equation. So I can use this to find g. Because I said earlier that the slope of my model, according to this, the slope was 1/2 g. So this means that g is 2 times the slope from my model, which would be 2 times 4.78, would be something that is much too hard for me to do in my head. 9.56 meters per second squared. And I know that's the units because g is 2 times the units of my slope. And what was slope? Slope is rise, which was meters, divided by run of my graph, which was squared seconds. So it all works out. And notice g is actually 9.81. So usually I'm picking reasonable experimental values here. This seems pretty reasonable to me. Wow, a lot of stuff here in kinematics. So last thing I'll do is we'll do a quick cut, and I will show you just this once how to do this entirely with Desmos. You do have to write all this out in your free response booklet, but I will show you why we should use Desmos for this and don't do this by hand. It is definitely possible for you to just calculate the slope by hand, by the way. That's allowed. I just think you're so error prone if you do that. I know I can't count grid boxes, so I just like to do it in Desmos. I'll show you the tied in true method. All right, we're here in Desmos. So this is going to be my quick linearization tutorial. So this was our data for h and t. So again, you can just type table, or you can click like the plus and a table will show up. And you need these subscripts to make everything work. So my first thing I would do is I would rename the columns. Instead of x and y, name it something, a letter that's more reasonable for your scenario. So these were heights, and these were times. This just helps me keep it organized. Now, what this magnifying glass does is this zooms in on your data, and this is pretty clearly not linear. So this button just adds a regression. Like, this isn't a terrible best fit line, but we know that this is not right, right? If we get rid of this, like this is clearly not linear. So what we did is we said our model is 1/2 times gt squared. I'm just writing that here just as a reminder. No, stop that. So what we said is that since h was equal to 1/2 gt squared, we said a reasonable thing we could do is the h, that can be one of our variables, and t squared can be our other variable. So we said that on the y-axis, we wanted to put h in a box, but not h, it was h1. You have to be remembering to do the subscripts. And then our x-axis was t1 squared. Sorry, I gotta look around for my typing here. So now what we can do is we can go down and we can create a new table. So we can create a new table here just by inserting table. And I like to call them capital Y and capital X for my linearization. So we have capital X, we have capital Y, and you should always zoom in on your new regression. Yep, that looks pretty linear to me. And then Desmos has a button that you just click it and it adds a regression. Boom, got my best fit line. And it spits it out in y equals mx plus b format. There's your regression equation. We see it matches. And in this case, I said 1/2 g is the slope. So if 1/2 g equals slope, then 2 times the slope is equal to g. So my experimental g is 2 times this number, which is the same thing we got earlier. So this is how you use Desmos to just do the AP Physics lab question. This works for basically anything. So again, step 1, do the raw data, rename it, make sure you have subscripts on these or Desmos won't recognize them. Then might help to just have your model here just so you know. Then define your new y and your new x, make a new table, do the regression, and solve for the quantity of interest.